welcome back. Alright, so today we're continuing to talk about geoengineering solutions that might be able to be a way of solving our very serious climate change problem. And we've talked about solar radiation management strategies, which the physics were good. There was problems, there were advantages and disadvantages. And we've been talking about carbon cycle engineering, and particularly so far I've talked about trees and planting trees. But that's not the only carbon cycle engineering strategy. Another way we could do this is just by working on fertilizing the ocean. Now, this is something you may or may not be familiar with. Let me explain what's going on here. When we talk about fertilizing the ocean, what we're specifically talking about is a strategy called iron fertilization. Iron fertilization is this idea of deliberately introducing iron into the upper ocean to stimulate a phytoplankton bloom. This is the reason why, let's see if I actually say that here. A lot of the oceans are deficient in iron. And in fact, it can be shown that in lots of parts of the ocean, iron in the ocean water is a limiting ingredient for production of phytoplankton. Okay? That if there would be more biological activity in these surface waters if there was more iron available. I mean, they need molecules of iron in their molecules, particularly chlorophyll, in order to have their processes. So the idea is you're to intentionally enhance the primary biological activity, which will produce this phytoplankton bloom, which then benefits the whole marine food chain. And the idea is then that eventually these materials transfer carbon from the surface waters down to the deep ocean. By and large, the phytoplankton live in like literally the top, few inches of the ocean or something like that, where the sunlight penetrates the most. They are getting their carbon dioxide from near surface waters. That is carbon dioxide that has dissolved into the ocean from the atmosphere. You're effectively extracting carbon dioxide from the atmosphere, storing it in these cells, these phytoplankton cells, and then things eat it or whatever, and then something eats them, and eventually it is deposited as waste, which falls generally down to the bottom of the ocean. And suddenly you've transferred carbon from the atmosphere into the surface layers of the ocean, and then ultimately down into the deep ocean. This is a way of removing carbon dioxide from the atmosphere and effectively disposing it into the deep ocean, which is another reservoir of carbon in the carbon cycle, but has the carbon stored down there has a residence time on the order of hundreds of thousands of years. Okay, eventually very deep currents will transfer that carbon up in form of upwelling along coasts, but that's a very long period of time. So this is an idea that we can use whatever is a shortage, whatever is the limiting ingredient for biological productivity in an area of the ocean, enhance it, and then stimulate this cycle. And this has been done in a research sense many times. I mean, they have ways that they can add iron to... I'm not a chemist, so I don't know exactly how they do this. It's as simple as iron filings. Is it iron oxide? I actually have no idea how they do it, because iron solubility is a real problem. But you can supply iron to the surface waters, and you get these iron-deficient waters to have more biological productivity. And this idea is what is more broadly called a biological carbon pump, where you are... This is different than like sequestering carbon using trees. Here you're using the biological systems to transfer carbon from one reservoir to another in a more permanent way. So again, you can see the diagram here. The ship offloads iron, and then the iron causes the phytoplankton growth. Dead plankton sink, and or fish poop sinks, and or dead fish sink. And then some of that reaches the depths where the carbon stays for, it says 100 years or more. It can be vastly more than that. Tens of thousands of years, potentially. This is a pretty smart idea, and it fits into a broader category of these kinds of climate geoengineering, carbon cycle engineering solutions called biological carbon pumps. But this is certainly the most well-known about these. When these were first being researched a few decades ago, the idea came to people's minds that hypothetically a company could do this to earn so-called carbon credits. You guys mostly are environmental science majors, and you either have had classes about the economics of like carbon markets and so on, or you will. But anyway, regardless, you have this vague idea at least that there are ways to earn carbon credits and sell carbon credits on the so-called carbon markets. And there was this notion that this should be a thing that companies can do. There should be economic incentives where they would earn carbon credits for doing this. To go out into the ocean, dump iron oxides or whatever it is that they have to do, document that there was an algae bloom that produced, and based on the geometry of it and the measurements of it, it should have sequestered this much carbon dioxide, and they would get carbon credits. And they could sell those carbon credits. There would be an economic model around here. And there's no doubt about it that, there's a demand for such a thing. I mean, the countries that don't meet the demands of the Kyoto Protocol are always looking for somebody who's got carbon credits to sell. It makes sense. So the economic advantages of doing this are huge, and the incentives are huge. But in practice, this cannot be done. Not that it wouldn't work, but there's a lot of environmental concerns about exactly. This is not a simple thing. This is a little bit like picking the winners. And there's a real good environmental reasons why they don't allow it. At the present time, international law does not allow this except for research purposes. This is in fact legally considered dumping if a company goes out and does this. There's penalties involved. They don't get carbon credits for doing this. But for approved research purposes and so on, this is a thing. This is allowed to be done for research purposes and so on. There are other parts of the ocean that are not necessarily carbon limited, but maybe phosphorus limited or something like that. And you can apply phosphates to the ocean or whatever. Okay, the point of the idea, you get the idea though. Stimulating the biological processes in an environment by adding whatever nutrient is deficient is a strategy. You could do that, and you can envision other ways in which it could be done too. Now, that isn't currently allowed except in research contexts. On the other hand, something that is allowed is air capture. Now, air capture is what I thought the future of carbon dioxide management in the atmosphere was going to be when I was a lowly atmospheric science student decades ago. I envisioned something very, very similar to what you see on the background of this slide here. I was envisioning that someday Dr. Shragiko was going to be building these carbon harvesters that actually capture carbon dioxide from the Earth's atmosphere. And they remove that carbon dioxide that is already in the atmosphere by some technique. Now, I have to admit, when I was a student, I thought somehow it would be filtered out. I didn't really understand how gases work, apparently. But there are chemical mechanisms by which you can do this. I mean, scrubbing one gas from a mixture of gases is a thing in physical chemistry. And like we scrub water vapor out of methane when we extract natural gas from the atmosphere, from a natural gas well, or we extract. Removing one gas extraction from a mixture of gas is a thing. There are chemicals that can be done to do this. And so you can kind of picture how this could work and how you could have some kind of system that air was flowing into, and you have some kind of system here of which a capturing solution of chemicals flows through that, fan or whatever, and you end up with a solution that is rich in carbon dioxide, and then there would be a chemical scrubbing system that has to be powered by energy that extracts the carbon dioxide, and the solution goes back in through the cycle here. And again, this is not exactly novel. It might be news to you because you might not have had PChem. It might not be news to you because you don't know much about like chemical scrubbing of, different gases, flue gases and so on, but this is a thing. This is a thing. This is something people go off to chemical engineering grad school and they learn how to run these things, and it's a thing. It exists. Or does it? Well, I mean, broadly, the strategy of scrubbing gases from mixtures of gases is the thing. But what I'm noticing, when you actually do like a Google image search on air capture technology, most of the images that you find of, what you're picturing in your head where the wind is flowing through and, I think this looks like what we were looking for, they're almost always computer images. They're renderings. I don't know that there's even that many demonstration technologies of such things, but they do exist. But the vast majority of them, if you find it's a company looking for investors so they can build such a thing, or it is a research group looking for funding, trying to figure out if they can build such a thing. At the present time, this works in the sense that it can be physically done, but the economics of it are bad. It currently takes an economically prohibitive amount of energy to do the scrubbing of the carbon dioxide from that solution, that chemical solution, on that side of the cycle. So, you have to purify the solution that goes then back through the cycle to capture carbon dioxide from the air. It is currently economically prohibitive to do such a thing, although one could envision maybe through solar or through wind, one could find ways around that. But the other problem is we don't have really any kind of plan about where we're going to put all that carbon dioxide anyway. As you might remember from, I believe it was in the second module, we talked about the fact that where are you going to get rid of carbon dioxide anyway? There's not really great solutions all of the solutions are complicated. They involve things like injecting the carbon dioxide into coal seams that it can't be exploited, or into depleted salt mines and things like that. All of which is expensive and complicated. We don't really have a good economic model for such a thing. Not for lack of trying, though. Clearly, a number of startups have figured out ways to make this happen and get the carbon dioxide out of the atmosphere. I happened to find this particular article online that kind of caught my attention. But the economics of it are not good. Ultimately, this is a big problem to figure all that out. That particular article talked about a company called Carbon Engineering. And Carbon Engineering was trying to build plants that suck millions of tons of carbon dioxide out of the atmosphere. And they were looking for governments to pay them to do this as a way of meeting their obligations of the Kyoto Protocol. And there were other companies in the system too that in the article were trying to do it, and they were trying to figure out how to transform this carbon into ways that they could do something with. One solution being use energy to use this carbon as a way of storing energy in the form of a fuel, where you're effectively making a synthetic methane or a synthetic petroleum product or something like that. For example, they actually talked here about a particular Swiss company that actually made synthetic diesel out of it. Okay, that is an interesting idea because effectively these carbon molecules become a very effective way of storing energy. You could use a renewable source of energy like wind or solar or even, well, not necessarily renewable, but like nuclear. Use that energy to assemble diesel molecules from this carbon dioxide that you captured, and the diesel is a very energy-dense way of storing the energy. And then you burn the diesel and it goes back in the atmosphere, but hey, we have worse ways of storing energy than building diesel molecules out of carbon dioxide, okay? Batteries are expensive and environmentally messy. We have a variety of ways that we store energy that are not as good as this. But all of these startups have practical business models that have problems. No one's going to be willing to just pay them yet to remove carbon dioxide from the atmosphere. At the present time, the technologies of these air capture facilities, it's more expensive than just paying the penalties to the United Nations under the terms of the Kyoto Protocol. And I mean, in the long run, we couldn't find ways to make this work, especially if we could find better ways of getting rid of this carbon dioxide. I can't remember if I talked in a previous lecture. You might be seeing these ads online for these mattresses that claim to be made of carbon dioxide. What it actually is they capture carbon dioxide from the atmosphere and use those carbon dioxide molecules to make a particular synthetic resin. I think it's something related to polyester. I can't remember. But effectively, it isn't like your mattress is full of carbon dioxide. There's all kinds of reasons why that would be a problem. But the plastics and the synthetic materials that make up the fibers were made from carbon dioxide. And there's some measure of smarts to that because mattresses cost a lot of money by the pound. And so I see where they're going with this. It's a smart way of taking what they harvested out of the atmosphere, carbon dioxide, and using it as a resource. It's smart, okay? But there's no doubt about it. Air capture is a problem. Air capture is not a technology that's going to work out soon. There's just no viable economic model. They are way off in terms of their costs of just removing the carbon dioxide and pumping it into the ground. No, it's way cheaper for the signatories of the Kyoto Protocol to just pay the penalties rather than pay these air capture companies. They're not able, they can only make things like artificial diesel or the synthetics in those mattresses or whatever with big government subsidies. Okay? They're nowhere near a standalone economic model. There's of course also this problem of in general what to do with the carbon dioxide that they capture. There's only so many carbon dioxide mattresses to be made. They're going to have to find other ways to get rid of that carbon dioxide, whether that's actually deposited into the crust of the earth or whether that is some other chemical brilliance. At some point they have to figure out a different technology here. The other thing is that this carbon capture stuff this air capture stuff is pretty slow. It is just nowhere near the industrial scale at which we add carbon dioxide to the atmosphere. Again, keep in mind all these trains of coal and all these tankers of oil. You'd have to be removing carbon dioxide at about the same rate. for this to be working. There's just no, the process is too slow. It requires too much of a long-term political and engineering and economic solution to get it up to any kind of effect. Again, this could be a part of the mix of the solutions, but it's not going to solve the problem for us. And it fits into a collection of a large number of these similar kind of strategies where we could have ways of removing carbon dioxide from the atmosphere in a carbon cycle engineering strategy. Peat, I don't know if you guys know what peat is, but peat is kind of like mostly decomposed material that sits at the bottom of bogs. As it happens, where I live in Indiana, there's a lot of peat bogs. And, you know, they're just sort of swamp, it's kind of a swampy mess, and at the bottom of it you get this organic material that, if it were eventually crushed by large layers of sediment and so on, would eventually form coal. But that's like on the order of geologic time. But there's no doubt about it, peat stores a lot of carbon, okay? It's a lot of partially decomposed vegetation material. It's kind of like permafrost that hasn't decomposed. And, well, peat is a thing. We understand peat pretty well. We could engineer peat. We could make ponds that produce peat and store... Well, that sounds terrible. I mean, don't get me wrong, it sounds like it would work, but do you think we can possibly... I didn't even bother doing the math to see how many ponds of peat we would need to produce, how much agricultural area would be taken up. I think it's fair to say we're not going to do that on an industrial scale. For that matter, wetlands do very much the same sort of thing. They're not quite as efficient at transferring carbon into the earth as a peat bog is, but the basic idea that they accumulate carbonate materials over long periods of time is a good one, and wetland reconstruction is in general a good idea for environmental reasons, but again, for climate change, this is probably not our highest priority. In general, there are lots of agricultural reforms that can help. Soil is a complex mix of inorganic and organic materials, living materials and dead materials, and depending on how you manage your soils and what chemicals you use, your soil holds radically different amounts of carbon. That is something that a farmer could make choices about. That is something that like a government could make choices about how they economically incentivize farmers. That's a thing. We could make choices about that, and potentially every acre of our agricultural lands could be making a difference with regard to climate change. That's not entirely a terrible idea. There's a whole story about burial of biomass. Now, you guys did a discussion in the class about that, where we talked about, you know, what if you just grew stuff and dumped it in a hole? Or, well, let's talk about that for a minute. I mean, you could grow alfalfa, which would be extracting carbon dioxide from the Earth's atmosphere and storing it in the form of leaves and stems, and then just have a big deep hole and you dump the alfalfa in, and then you sealed it all up. And that would be a type of carbon sequestration that's called burying of biomass. In general, I don't think there's any viable, you know, proposals to do that on any kind of industrial scale, but we do kind of do that already with regard to, like, yard waste, okay? We talked in one of the discussions about the fact that there's different strategies about how to deal with yard waste. One of them is to compost it, another of them is to put it into landfills and let it foster the development of methane, but another strategy is just dig a deep hole and bury the stuff. It's a carbon sequestration strategy. It turns out to not be a particularly good one, because grass clippings and sticks that come down in a strong wind and stuff like that don't actually add up to that much carbon. But it could be done. Biochar burying is another strategy, where you would be using burnt biological material. There's still a lot of carbon left behind, you know, in like the ashes from production of charcoal and stuff like that. Again, this has the advantage of it's a fairly carbon-dense material, and so you could be burying these materials in the ground as a way of sequestering carbon that otherwise would be ending up back in the atmosphere through the action of bacteria and so on. But in general, there's a whole menu of these options, each individual one of which probably is not going to save the world, but taken together might be a strategy to postpone the dates at which we reach certain climate targets and so on. Now, before we go on to the third part of the lecture, let's answer two quick questions. Question 3. Which of the following is an example of a biological carbon pump? A. Planting trees in the playground at school, which transfers carbon dioxide from the atmosphere to the wood of the tree. B, stimulating the growth of plankton, which transfers carbon from the atmosphere into the deep ocean? Or is it C, developing genetically modified bacteria that break down plastics rather than letting them accumulate in the ocean? Hey, they all sound like good things, but only one of them is a biological carbon pump. Make a choice from those three options to get a little feedback before you move on to question 4.